In the last video, we introduced the Gibbs free energy and explained that it can be used to predict the spontaneous direction of a number of processes. We had an expanded form of this equation based on the definition of the Gibbs energy that let us qualitatively describe protein folding. But let's wrap things up today with quantitative use of the Gibbs free energy by applying this equation to batteries. And besides, modern engineers should have at least some insight into ways humans can generate work besides combustion. Okay, so we have some idea that in batteries there's some energy that's being stored in here, but it's being held back somehow. And all we have to do is create a little conductive path from this end to that end, and the energy that's stored in here will be spontaneously and irreversibly released. Early on in class, I asked, what is the form of this energy? And most everyone could say something like, well, it's chemical energy. Okay, but what really is chemical energy, and how do we calculate how much of it we have? That depends on the chemicals we're starting with and the reaction we're talking about. How we begin is with the idea that the Gibbs energy is a state function. So, like all of the other state functions we've worked with, we can calculate a change in Gibbs energy of reaction by exploiting the property of state functions and referencing values to some agreed upon standard states. So the reaction Gibbs energy, just like enthalpy, entropy, and internal energy, is going to be equal to the sum of the Gibbs energy of formation of the reactants minus the products. And just like our other state functions like enthalpy and entropy, we can go look up values for this Gibbs energy of formation in the table somewhere. Thank you, NIST. And notice that if you can't find Gibbs energy of formation values, then we could assemble them from enthalpy and entropy values. If the value of the Gibbs energy of reaction is negative, we call this an exergonic reaction. It proceeds spontaneously, and humans can use such reactions to get work out. If the Gibbs energy of reaction is greater than 0, we call it endergonic. And to make endergonic reactions go, the human has to put work in. So we're going to do a sample calculation for the type of system that we're interested in, a battery. And the particular type of battery that we're going to start with is called a Daniell cell. I'm choosing this type of battery for its simplicity, but also for its historical relevance. The Daniell cell was invented in the early 1800s, and it served as the basis for the historical definition of the volt. The reason being is because by the late 1800s, the Daniell cell was being used as a voltage source for most telegraphs. The version of the Daniell cell that I've written here was developed in the mid-1800s, and it's called a gravity cell. What it is, it's a copper electrode suspended in a copper sulfate solution. And you can see that the wire connecting this electrode goes up through a tube, all exposed to copper sulfate, passes through some kind of load that we would like to power, and connects to a zinc anode. And that zinc anode is suspended within a zinc sulfate solution. So to calculate the Gibbs energy of reaction, we have to figure out what reaction we're talking about here. There's going to be reactions that happen at the cathode and reactions that happen at the anode. We call those half reactions, and we have to assemble half reactions to come up with the full reactions. So let's use this as an example to go through that process. On this side, let's say 2 electrons magically show up at this copper electrode. If that were to happen, then it could be the case that some of this copper sulfate, which I've written all together here but is actually existing in solution as separated copper and sulfate anions, just the same way sodium chloride breaks apart in solution. So if 2 electrons show up here, some of the copper sulfate, some of these copper cations, will incorporate these 2 electrons to become metallic copper, and it'll actually electroplate copper onto this electrode. When that happens, these sulfate anions are now all alone in the world. They do not have their counter-ion partner, and they are free to diffuse. So what will happen then is that these sulfur anions will diffuse up into the zinc sulfate solution. Now let's say a sulfate anion was to be hanging out near this zinc anode. That zinc anode, which was a metallic solid, can react with that sulfate to make zinc sulfate solution. And in the process, liberate 2 electrons. So notice that there are 2 things that are being exchanged between these 2 reactions. We have the electrons that are being produced at the anode, passed through the load, and appearing at the cathode. But we also have the sulfate counterions that are able to diffuse from one side of the cell to the other side of the cell. So to figure out what reaction I need to calculate to get the overall Gibbs energy, all I do is I take every term on the left side of these reactions and I sum them up and put them on the other side of a reaction arrow with everything that's happening on the product side. So let's go through and do that. I've got 2 of these because I've got one here and one there, 2 of the sulfates. And what we can notice is that some things on either side of these reactions are just being transferred. They're not being consumed. The electrons and the sulfates are transferred but not consumed. So they cancel each other out on either side of the reaction. And the net reaction that I'm left with is copper cations with zinc metal becoming zinc cations with copper metal. And this is the reaction that I should use to calculate my reaction Gibbs energy. If I go look up the Gibbs energy of formation in the table, the values that I get are 65.49 kilojoules per mole for copper. Zinc is the agreed upon standard state for zinc, so we call that 0. The zinc anions are minus 147.06. And copper metal is the agreed upon standard state, so it's 0. So what you maybe notice from this reaction is that really what is driving the spontaneous change is the difference between the Gibbs energy of formation of the copper cation versus the zinc cation. And you can see that the Gibbs energy of formation is indicating, its negative value is indicating that the 2 electrons would way prefer to be on copper, and that's what's driving this reaction forward. an interesting thing to go look up now is what is the Gibbs energy of formation for lithium ions? And from that value, you might get an indicator about why lithium batteries are so popular. Okay, so we have this reaction, and if I sum up those values, I end up getting an answer that the Gibbs energy of reaction is equal to 212.45, negative 212.45 kilojoules per mole. So now let's go from this Gibbs energy of reaction to the voltage that I get out of my battery. I'm not going to derive that equation, I'm just going to write it down, and it's quite simple. The Gibbs energy of reaction is related to the voltage in a battery by the number of electrons that get transferred in from one half reaction to the other half reaction. So in the example we just showed, it's 2 times Faraday's constant times what's called the cell potential. So for the Daniell cell that we just calculated, what we're interested in is the cell potential. Although I will note, you can solve this equation for either the cell potential or the Gibbs energy of reaction. So presumably, if you measured voltage in an electrochemical cell, you could use that to validate a Gibbs energy of reaction that you just calculated. But for the Daniell cell, let's just write out what these numbers are, solving for the cell potential. Using the Gibbs energy of reaction value I calculated before. There are 2 electrons transferred. Faraday's constant is equal to 1.602 times 10 to the minus 19 coulombs. And notice that there's a per mole quantity here, so we actually have to consider coulombs per mole, so we should multiply this by Avogadro's number. And if I multiply all of this out, actually before I multiply it out, I'm going to take a moment to talk about units, because we've got joules over coulombs. So early on I mentioned that this Daniell cell was used as a definition of a volt, but in recent times the value of a volt was just changed. Actually, on the 20th of May, this is an aside, I'm going to go over here. On the 20th of May in 2019, the 7 SI base units were redefined. This happened in your grown-up lifetime. The volt is not an SI base unit. It is what's called a derived unit, and 1 volt is equal to a kilogram meter squared per second cube per amp. So let's take these units and break them apart into the SI base units. The value I'm going to get here if I churn all those numbers is 1.10, but then thinking about just the units on the top, I get kilograms, meters squared per second squared. This is from joules per mole. A coulomb in SI base units is an amp per amp times second, an amp second. And we have Avogadro's number. So if I go through and cancel my units, then I end up getting 1.10 kilograms meters squared per second cube per amp, which is the same as my unit of the volt. So if you're on a long road trip or sitting around a campfire with friends, I totally recommend you read about this 2019 redefinition of SI units. It was a massive international effort. Fascinating stuff. Okay, and this is close to 1 volt. but not exactly because of this redefinition that happened. Alright, so what happened in this video? What should we say to recap? There is a quantity called the Gibbs energy that can predict the direction of spontaneous change. And we no longer need to concern ourselves with the whole universe or the surroundings because this quantity pertains to the state and it pertains to just the system. It also represents the amount of useful energy we can get out of a system. Qualitatively, we used it to describe protein folding, but what we learned today was how to use it quantitatively, and specifically how to apply it quantitatively to calculating the Gibbs energy of reaction to determine if any given chemical reaction can store chemical energy for us. If a given chemical reaction has a negative Gibbs energy of reaction, it's exergonic, it'll proceed spontaneous and it would be a good reaction to store chemical energy. And then humans have gone around finding a whole bunch of exergonic chemistries to store within batteries. And we learned about how the Gibbs energy of reaction for some overall exergonic reaction in a battery can result in a voltage. Through this equation.